I didn't like the 80s pitch. Alright. Is this forward? Sorry. Okay. So I did Newmark's method of structural dynamics, and that is Nathan Newmark. First off, just a little bit of history on him. He was a professor at the University of Illinois at Urbana-Champaign, and he wound up being the head of the Civil and Environmental Department. Also, this was officially published in the ASCE in 1959. But what I'm going to go over today is a general procedure for solving structural dynamics problems. This is mostly used for high impact or shocks, such as earthquakes or missiles or possibly projectiles from tornadoes or hurricanes. Generally speaking, how is it performed, kind of breaking it down, because the first time I looked at this, it was very difficult to understand. But when you look at it, it's a lot like the equations for physics that we use. You have usually a first displacement and a second displacement. You've got time. In this instance, you have a beta and a gamma, which we use for damping, and I'll explain that in the next slide. You have different equations to find d2 or v2 based on what variables you have, and then how to find your change in velocity and your change in acceleration. And then it works for applied external and internal forces on members. So this is the general equation for the whole thing. It's saying that the mass matrix of whatever frame or system you're using times the acceleration, generally speaking, matrix. We're just going to use a single acceleration, plus the damping matrix times the velocity matrix, plus the stiffness matrix times the displacement matrix is going to give you the force. And the mass matrix is always going to be in kips or pounds times second squared divided by inch, which if you have your acceleration matrix, that's going to be inches per second squared. So all of those are going to wind up canceling out to just kips, and C is going to be kip second per inch. So this is a little bit more information on gamma and beta. Gamma is usually equal to 1/2 for estimations, although you can change it. And beta can be different. I've seen values anywhere from almost 0, which is considered no damping, to 1/2, but they say the best range is between 1/4 and 1/6. 1/6 will give you a linear acceleration, and 1/4 will give you the average acceleration. And of course, they don't necessarily have to be that, but you could find an average acceleration from a linear acceleration or other accelerations just to make it easier on yourself. So this is a general, I guess, step-by-step process of how to do it with some of the more complex problems. But like I said, we're just going to use one that's for a single member. So, if you're given a mass matrix, acceleration, basically if you're given all of these, you want to find the second set of forces. And we're going to do it for a linear acceleration, so gamma is 1/2 and beta is 1/6. Here are your general equations for acceleration, your v2, and your d2. Obviously we have equation 1 and equation 2 back up top. Equation 3 for the second velocity, and equation 4 for the second displacement. So if you do 2 into 1, it gives you basically the change in all of those acceleration, velocity, displacement, and force. And then 3 is going to give you delta V is equal to V2 minus V1, which is just change in time times the first acceleration plus gamma times the change in time times the change in acceleration. And then for U, it's generally the same thing. I'm not going to keep running through these one by one, but you have your change in acceleration and your change in velocity from equations 6 and 7, which are right here. And then if you plug those two equations into equation 5, you're going to get your K prime is just your change in displacement times your change in F prime. So now we have values, which the values for M, K, and C are given. If you had some sort of modeling software or another problem, you would be able to find them, and they might be matrices, but like I said, we're just doing it for a single member. You have your desired change in T, which is 0.1 seconds, and we have our gamma and our beta established already. So then we plug in for K prime from equation 11 right here. Using all of those values, we get 114.5. And we are able to find our acceleration because we have all of those as well. Our change in F is going to be this equation, or F prime. Our change in X is going to be that over K. Our change in V, change in acceleration, and our X2, which is how we find the next step. So this is a data table for up to 1 second of everything. And it has our force, the acceleration, the change in force, change in force prime, the change in displacement, the change in velocity, acceleration, and then the velocity and the displacement. So, how can this be used? This can be used from anything such as a simple spring like we saw in physics and dynamics. If we wanted to get a more, I guess, detailed and accurate solution. Anywhere to buildings that are hit by large projectiles or where we cannot find the forces, or we have to design for the forces in extreme situations such as earthquakes. And then just, I had to find out what damping was because I kept reading about it and I wasn't really sure, but it's a reduction of like forces on the frame based on consolidation. And I attempted for like a week and a half. There is a program for it. It's on MathCAD, but if you try to download it and run it, there's some sort of error in the code, and I hate MathCAD, so I just gave up eventually on that. But do you guys have any questions?